so yesterday we did this example. We did what's the area under the curve from x1 to 9. We did that example. So we did rectangles from the left. Remember, it was 168. And then when we did the right, we got a 328. The midpoint, we had a 240. And then on the trapezoids, we had a 248. So we did all that work yesterday. Okay, so we're going to figure out what is the actual area. Okay, so I've already set it up here. When you do an area, you do this. I'm going to integrate this equation with respect to x from 1 to 9. That's what that language all means. Okay, so I'm going to put a square box like that, which means now I'm going to do the actual integration. Okay, so this equation, I have to go 1 up, so it's a cubic, and I take what was in front and divide by this. So there was a 1 in front, and I divide by that. Okay, so now to get the area, I plug in a 9, subtract, I plug in a 1. So this is 243, subtract 1/3. So then that's the actual area. Okay, so you can see when we did our estimation stuff, our midpoint and our trapezoid were pretty close estimates. Okay, so this example on the bottom here was an equation of a line. So you can see that I've done this for you. So I integrated it. So when there was a 9, the original was a 9x. On this, it had to have been a squared, and you can see me taking this divided by this. Okay, so then I need to go from x of 0 to x of 3. So I plugged it in, and I got 13.5. Okay, on this one, I also just used geometry because it was a perfect triangle. Okay, it doesn't work on a parabola, but I could do a perfect triangle, which is half of the base in height. So if this was 9 and this is 3, so what's a half times 9 times 3? So that ends up being the same. Okay. Some of this stuff you're going to have your background graphing knowledge for. Okay, so when I looked at the equation 6 minus the absolute value of x, I did all of the pre-calculus stuff. So the absolute value of x is this graph. I guess there would be arrows on it, but okay, this is the absolute value of x because y equals x is that. And then what happens when you absolute something? Remember? Positive stays, negative reflects. Okay, then since there's a negative in the front, what does a negative in the front of a graph do? Reflects it. And then there was a positive 6. So what kind of transformation does that do? It shifts it up 6. So this is my graph, and I want to get the area from this to this. Okay. So on this, I'm going to use a geometry shape. What is the base length? 12 times the height. What's the height? 6. And since it's a triangle, I have to divide by 2. So the area should be 36. Okay, find the area from this function. So when I graph y equals 5, what do you know from previous experience? It should be a flat line. So all the way from 0 to 5, what is the area? Okay, so this is a geometry shape. So you can actually use just geometry here. It's a rectangle, that's 5, and that's 5. So the area should be 25. Okay. Now let's do some integration. So how do you set this up? How does it look? How does your format look? So you're going to integrate this equation with respect to x. And you're going to go from an x value of 0 to 5. So that's how you set up what it needs to look like. Okay, so can you anti-derive this? So what did the original look like? Did you pick 5x? Okay, because when you derive that, then it would just be 5. From 0 to 5. Okay, now I'm going to plug in a 5, subtract, plug in a 0. So 5 times 5 is 25, subtract 0, the area should be 25. That's where you get it from. Okay.
We're not gonna, whenever the one above it, like with the absolute.
With the absolute, I don't have a rule for doing the antiderivative of. So that's why I didn't. So you won't see that. Okay. Ready? We're going to, from 2 to 6, find the antiderivative. You ready? This squared would have started as a cubic. Take what's in front and divide it by the new exponent. So 1, or you don't need to write it. This would have started as a squared. Take what you had and divide it by the new exponent, which makes it 2. You can always check with your derivatives. If you derive this equation, does it make you go back there? Okay, you're faster at that. Okay, plug a 6 in. Plug a 2 in. Okay, so you're going to have to plug a 6 through it, plug a 2 through it, and it's subtract. You're always going to be subtracting. Okay, what do you think here? 6 cubed. This one is 288. Mine is 16. Okay, this one is going to be a little bit of a trickier one. Okay, so we need to start with our exponent 1 higher. So what is that going to be? So 2/3 plus, I got to be 1 higher than that. So how do you figure that out? What do you want to do here? Should we think about this as a 3/3? So this would have started as a 5/3. Okay, now originally there was a 1, and we would have to divide it by the new exponent. Okay, what happens here? Flip, multiply, which makes 3/5. Okay, you're fast at checking. So does this times this make 1 and then lower 1 exponent? Does it work out? Yep. And then this would be 5x, because you have to go up an x. Okay, so now that's the antiderivative. So we can put a box there because we've done that process from 1 to 4. Okay, run a 4 through it, run a 1 through it. Okay, and then you'll have to get some numbers there. Running a 4 through it. You might want some brackets on some things. Let me know if anybody's matching any of my numbers here. I see some of you not doing it. Anybody match? Heidi, you're doing it. Rory, you did it.
Yeah,
You match? Okay, I'm gonna skip number 3 till tomorrow because I see something on there that you don't know how to do yet. So I'll do that one tomorrow. Let's do number 5. We can do that one. So on your homework, maybe I'll pick out some for you. Okay, we're going to integrate. So let's antiderive this thing. Okay, so this one, go up. So the original was an x4. Take that divided by that, which makes 1. This original would have been a squared. Take that divided by the exponent, so -8 divided by 2. Okay, and again, just double check quickly. Drive it. Does it make the original? Okay, plug a 6 in. Subtract and plug a 3 in.